deeper in the past, closer to the Big Bang, the primordial nucleosynthesis. So you keep pushing to earlier times, higher temperatures and higher densities. And what's going to happen there is going to start having some annihilation and pair creation equilibrium that involves protons, electrons, neutrons, and neutrinos. And these are the possible nuclear reactions that can happen. As the universe expands, it gets cooler. By the time it gets to the 10 billion degrees Kelvin, roughly 1 second, the whole thing pretty much freezes. Now, there is a difference in the number of protons and neutrons because they have slightly different mass. And because they have slightly different mass, there's going to be slight difference in their distribution, thermodynamical distribution. And so when this is over, you're going to have certain ratio of the number of protons and neutrons, and that ratio is telling you how much helium you're going to make. So neutrons decay at a lifetime of the order of 15 minutes, and that destroys them before they can interact with the rest of the hydrogen. And so when you go down to about 1 billion degrees, then there is really no more possibility of forming helium. So light nuclei formed before then are photodissociated by the gamma rays, which is progenitors of the cosmic microwave background. And so that's how the nucleosynthesis ends. It begins when the universe is at the right temperature so that protons and neutrons are the dominant particles, temperatures corresponding to giga-electron volts. It ends when it's too dense and too cold to fuse hydrogen into helium. And so you can do this in a very detailed fashion, and theorists produce curves like these. On the x-axis is a temperature. You can think of the temperature as a proxy for time, right? And on the y-axis is relative mass fraction of different things. So time is shown on the top axis, and so as time goes on, first you have protons and neutrons, and the ratio is given by the mass difference. And then a lot of things happen. You start dissociating nuclei and so on, and product is on the right when everything is frozen and clear, and you have still mostly hydrogen and then helium, and then deuterium and mass 3 isotope of helium, and just a little bit of heavier stuff. So this was actually seen as a failure of the Big Bang model early on because it can explain origin of chemical elements all the way up to helium, but not much beyond. But then people understood everything else is cooked up in stars and supernovae and so on. So Big Bang nucleosynthesis, which is based on the nuclear physics that we know, makes predictions. Predictions are the relative abundances of the light chemical elements, mostly hydrogen and deuterium, and 2 isotopes of helium, a little bit of lithium, beryllium, and maybe even traces of boron, but those are actually not very sensitive. So if you can measure the abundances of deuterium, helium-3, helium-4 relative to hydrogen, you can learn something about density at the time of the recombination, density of baryons, mind you. And the result is shown here. So for value of Hubble constant of about 70, which is 0.7 here, it will be about 4.5%. Amazingly enough, it's exactly the same value that's obtained from a completely different way of measuring it from microwave background fluctuations, which is atomic physics at a much later time. And the fact that 2 different measurements from 2 different kinds of physics agree so well convinced everybody that this is really the case. But this is essentially how this is done. What's shown here on the x-axis is density of the baryons at the time of nucleosynthesis. Today, extrapolate this since then. And on the y-axis is relative abundance relative to hydrogen. So different bands show predictions of the theory. They're not lines, they're bands because there's some uncertainty of the modeling and so on. And the boxes are showing you what's the actually observed value. And you can see that they agree pretty well. And the smallest box, meaning the most precise measurement, comes from deuterium. Deuterium is really easy to burn into helium. And so it's going to be very sensitive to the density of baryons. If you have more baryons, you're going to get rid of the deuterium. It has no chance of surviving. If you have fewer baryons, you can still keep some. And so this is why it's the steepest line and the sharpest measurement. Now, the way this is done, stars also make helium, so what do you do about that? So you look at star-forming galaxies and measure abundance of helium in their spectra. You also measure abundance of something else, like oxygen. Now, oxygen or nitrogen, doesn't matter, is made in stars and in the same proportion as helium. Right? So that line that you see out there is slightly tilted. Its slope corresponds to the ratio of how much helium you make for how much oxygen, and its intercept tells you how much helium is started with before there was any nucleosynthesis. So the intercept of this line is telling you what primordial abundance of helium was, kind of getting rid of all of the nucleosynthesis in stars. And it's about 0.24 by mass, and that agrees beautifully with predictions. The way we measure deuterium is actually done in the spectra of intergalactic medium as illuminated by background quasars. There is of the order of, a few parts in 10 to the 5 deuterium relative to hydrogen. And so what you want is a cloud of hydrogen sufficiently dense that you have a big signal so you can detect deuterium. Because of the isotope shift, heavier nucleus, Rydberg constant is a little off. The deuterium equivalent of Lyman alpha line is shifted relative to the one of regular hydrogen by 80-some kilometers per second. And by measuring the relative strength of those two, you can figure out what's the fraction of deuterium. When you, from spectrum and modeling of spectrum, you go back to this diagram and read off what is the baryonic density that corresponds to that ratio of the deuterium to hydrogen. This is actually a pretty safe way of doing it. It's not easy, but it's safe. And this is because deuterium is not produced by anything, maybe occasionally by chance, by spallation, by cosmic rays, but deuterium can only be destroyed through stellar evolution. It's hard to make it. And so in that way, by measuring the abundances of light chemical elements now or for past X billion years, we can actually learn something about the universe when it was millisecond to a few minutes old.